Okay, so I'll be talking a little bit about black holes again and galaxies and their formation, but now from the perspective of simulations, and also sort of shift into the very high redshift for the purpose of this talk and the time given. So I'll be talking a little bit about the issue of how we actually form the first very massive black holes at very high redshift, and what we can attempt to learn from just standard structure formation models. As it's already been emphasized, we of course, now that if we want to try and learn something about black holes, of course we're going to have this really big challenge of trying to resolve what's going on at the center of galaxies. And of course, if we look at the kind of scales that we're going to try and do in a cosmological simulation, a cosmological model, we of course understand sort of the dark matter behavior to some extent, at least at large scales, probably pretty well. Then we want to move into sort of all the issues that have been a great subject of this conference, and it always is, sort of the galaxy formation side, and now really moved right down into the very center to try and learn about something that a black hole could be doing in terms of growth and feedback. But this has been done. It's challenging, but of course it doesn't stop us. This is just an example from Roman simulations of a galaxy cluster. So this is the density, the gas density, which is color-coded by temperature. In one case, there's no AGN feedback implemented in the simulation, and in the other case, there is, which is the case here, and it's now, I think, pretty well established that there are some effects that, of course, you do have by coupling AGN feedback into galaxy formation models, structure formation models, that it'd be nice to try and understand more. So this is just an illustration. So what I want to focus on is a little bit about the early growth, and I'll just do a very, very brief introduction, and Lucio tomorrow will go into this in much more detail, maybe, right, into the physics. But how do we start? The story of these massive black holes? What are the seeds of these massive black holes? And this is not really the subject of any of the work that I'll show you. Is just more just as an intro, just to focus onto this. And what I'll be talking much more about is how maybe what can we learn about their growth. So there are pretty much two very popular scenarios of how black holes get seeded in galaxies very early on. We are talking about the first halos that collapse and can start H2 cooling. So redshift 20, halos of 10 to the 6 solar mass or so. They could be forming the first population 3 stars, the remnants of which, if indeed the first stars are massive, could be indeed massive black holes, seeds of the order of 100 solar masses or so. Another very popular scenario is basically direct collapse via gas dynamical processes. And again, I don't want to go into this in much detail, but we could, in some situation, we could bypass this and go straight into a black hole. So directly collapse the gas and end up with black holes that have masses that are typically larger than for population 3 remnants by a factor of 1,000 to 10,000 or so. So again, this is not any of the physics that we can much understand by doing sort of cosmological simulation, but it only constitutes our initial conditions. So say you have cosmological simulations and you start resolving the collapse of the first halos, then all you do, at least all of that we do for now, and there are more sophisticated models, more physically oriented, but you just place black hole seeds of this kind of range of masses, and typically we'll go up to more this sort of masses in newly forming galaxies. Okay, so this is all we have once we want to sort of understand the global growth. So some initial condition, and then what we're trying to understand, how do we get black holes that are as heavy as the ones that we heard today? We just heard about, but at the universe when it was at redshift 6, so the first sort of redshift, the first quasars type of objects. So how do black holes grow? They will grow by merging within each other, but this will not do very much by just doubling mass. We're not going to get in less than 1 billion years to such large masses. Gas accretion, of course, is what is going to be dominant. And that's why, this, of course, this is even tougher, perhaps. Associated with gas accretion, of course, we'll have some luminosity, so some output of energy from these black holes, which in some way or another will operate some form of feedback, which again is something that we're trying to understand. And of course, we can't in detail in large-scale simulations, but we're at least trying to understand the impact of that. So just to be a bit more clear, so what I'm going to be focusing on is, say we have this inferred massive black holes of 1 billion or 10 billion solar masses at redshift 6. So they're as massive as the ones that have grown to the same similar masses but today. So that's many billions years ago. So, and it's very easy to show that in order to grow these sort of masses at during this the amount of time that we have to redshift 6 or about redshift 6. So now the heaviest black hole is at redshift 7 or so. You need to sustain Eddington rates onto these objects at these early epochs pretty much throughout the whole time. So the question is this possible? Do the initial shallow potential allow this? Or how does it occur? Do we meet this condition? Or is there something really funky going on about these objects that we need to go out of our standard structure formation scenario to understand? So this was sort of the experiment, sort of very dumb, that we tried to play to start with. We want to try and understand these objects. These objects are in the early universe at redshift 6. They're extremely rare. They have space density of the order of 1 per gigaparsec cube. So this means that if you want to try and understand the growth in this kind of halos, you have to go to these volumes. So if you want to try and find the conditions that allow these sort of things. But within these large volumes, you really want to understand how the gas gets into the central galaxies. So you need to have as high resolution as you can, which also means hydrodynamics, because we're talking about gas. So this is an extremely challenging thing to do. Like if you just don't impose, you know, some kind of preferred halo where this can occur, and you can try and do it and learn as much as you can from it or not. So that's what I'm going to be talking to you about, some cosmological simulations. I will start talking to you about uniform volume. Of course, we see lots of simulation of zoom halos, and I'm going to use that as a sort of second step as well, which is much more in progress, though, so I don't have much to say. But uniform volume, so we do this sort of bold, sort of dumb thing. We do gigaparsec volumes and try and look within there, what are the places which are conducive of larger growth or larger inflows, and how is that occurring? So this is one of the runs that we did, sort of these gigantic things. So it's roughly a gigaparsec in volume, a bit less actually. It's just a really chunky, large SPH run with a mass resolution that is close to the Millennium 2, roughly. But much larger volume, if you're familiar with that. But I'm just going to show it to you if this works. Let me see what a snapshot of the simulation looks like. So this is basically what, if you display on 2D, what a gigaparsec looks like. It's extremely boring, and you may wonder why bother, of course. But OK, within there, you, of course, can zoom in. And I'm just using some software that one of our students that is developed at CMU to zoom into this density distribution in these very large volumes. And really what you're asking yourself now, say, is within this very large density distribution, which regions are, in fact, conducive to the growth of very large black holes. So there is a model in there that tells you how, sorry, this is a bit slow. So you can go and find yourself places where the largest volumes have actually grown, the largest black holes have actually grown, and then start looking at what kind of environments this happens. In order to know about black hole growth, there's a very, very simple model that, as I said, places a seed black hole particle at the center of a very early halo and follows a gas accretion onto it according to, of course, subgrid physics that you can implement. And this is one particular choice. You're basically just saying, you're looking at how much gas you have around the innermost resolved regions, and the mass flux onto those regions give you an accretion rate, which is in fact capped at Eddington, the critical accretion rate. And what you also include is some form of feedback, which is again very simple, because at these scales you can't really capture anything else anyway. And you're just saying that a fraction of the energy that is liberated by accretion, and it should be m dot there, some fraction that is a parameter, is coupled back into the surrounding medium and heats it isotropically. So what you end up with typically is then, besides the full structure formation scenario, galaxy formation, is some information about each one of your black holes that have actually been put there and have grown and so on. So you end up with a mass growth curve. So the mass of the black hole grows with redshift. And according to each of the black hole has its own history of accretion rate, its own light curve within this cosmological volume that you can go and look up and see what's happened to it. This is actually an early simulation. So let me show you a little bit of the environments of these very first black holes that have grown to large masses. So the first thing that we notice is that it is possible to grow such large masses of 1 billion solar masses or so. This is just one example. We go at redshift 6, and the black hole mass is a bit above 10 to the 9. This is the accretion history. This is an Eddington rate placed onto it. So what you see is that this black hole was steadily growing at Eddington up until some point where its accretion rate is quenched compared to its Eddington. And this is a result of the feedback. I'll show you the images related to these two phases. In the initial phases, we see this Eddington growth, and you can sort of get an intuition of how this gas is getting channeled so fast. We've talked about cold streams and cold flows. This is certainly visible even within these images without too much analysis. And in this quenched phase, we can see how the feedback, the temperature is shown by the colors in these images, which are density color-coded by temperature, starts affecting the halo, and in fact starts heating the gas within and outside the halo, driving a strong wind up to the point where a lot of the gas is ejected, but there are still some cold streams coming through there. So the accretion is not quenched. This is just another example, again showing the same thing. Another black hole that is one of these extreme growth, shows one extreme growth. And again, we see all this gas coming in, very high density blobs, right? We heard about this a lot. And again, up until some point, after which it gets quenched. And that's the point where really feedback starts heating the gas well above, outside sort of the virial radius, within and outside, and sort of sweeping it out, all the way out. So again, so what are we finding? We're finding indeed that the places most conducive for such critical growth are, in fact, these halos, the very massive halos that are sort of the first ones to collapse and grow at this redshifts, mostly by getting their gas in this cold stream mode. They have, of course, the highest densities. And of course, because the gas is coming in these cold streams, feedback is having a pretty hard time to couple to these high density blobs and actually disrupt them. So the growth keeps going for a long way. This is just to highlight, these are typical accretion rates. In red is some of these objects compared to some objects that are in a lower redshift simulation that goes to lower redshifts. Typically, the accretion rates are much higher, this high redshift, because the densities are higher, and there's more growth so the early growth is the fastest growth because the environment is the environment of the highest densities. And Colin, in the next talk, will talk a bit more statistically in terms of the sample about that. So we find ourselves in very high gas-rich density, but this gas-rich, the gas that is coming in through cold stream. It's very hard to stop this gas. It's very hard for any feedback to couple to it. And that's what we seem to, that seems what to be hinted in these large-scale simulations, okay? So if you ask yourself blindly in a large volume where you get most of the growth, is in this kind of conditions. The largest halos, they are growing by assembling themselves in this cold stream mode. And they have the highest gas densities and the hardest time for feedback to couple to this stuff. So in some sense, I'm sort of, and when you go and look, there's very few examples in which you have major mergers. So the first quasars are not necessarily, but of course, if there is one, it helps, the result of a major merger. That's not a requirement to get enough gas into it. It seems this is just showing another example of a large black hole mass. And this is just the main progenitor. And this is one case in which there is one major merger, but that's not responsible for a lot of the gas coming in. A lot of our objects, if you look at all the objects, the black hole, again, the main progenitors and all the objects that are merging into it, they're mostly minor mergers, as you, of course, know, as a lot of these blobs coming in through the cold streams, all this will be subhalos as well that will eventually themselves contain black holes that will come in, but there are not so many major mergers. So slightly more quantitative, of course, you can, you have the simulation, the model is pretty simple, so you can ask yourself, suppose I find myself at some redshift 6 with this 10 to the 9 supermassive black hole, then I want to know, really, how has the gas got into there? I can just say, okay, let me trace back all my gas particles that have actually contributed to the growth of this object back in time. And I'm not sure you can see that in these images, but this is what was done, and it's sort of displayed by this Y point. So we start at some redshift, and now I'm looking for the particles that have gone into this black hole mass back in time, and all of this gas was indeed residing on this large-scale structure filaments all the way into they came straight through into the Virial radius of the galaxies, eventually made it all the way to the very, very center. And you can also plot the temperature of this gas, again, sort of tracing it in time. So you find yourself with lots of very hot gas particles near the black hole at redshift 6. That's the result of the feedback that has heated them. But as you trace them back in time, you can find that all these particles came in very cold. It was very cold gas that came straight through. This is sort of indicates the virial radius of this halo, and way below the virial temperature. So in fact, you can measure that 95% of the gas that has actually gone into growing this black hole does belong to this cold stream phase. And you can do this for all the halos. Of course, now the question is, okay, I've done this in this huge, large volume, and a lot of you may think, okay, how does this map into smaller scale? So the resolution, as you could see from the previous plot of our cosmological simulation, this gigaparsec is in physical, is just sub-kiloparsec. Is like around just below 1 kiloparsec, which is actually really good for this cosmological volume of this size, but it's still not ideal, right, when we want to study the gas inflow into small regions. So you really want to go in further. So at this point, once we've sort of located, these places where we can associate large inflows into the center of the galaxy, like this object that I've already shown you, then you can, of course, do zoom simulations, and this is just one example of that one halo, and hope this way to get much further in. The question here, is this cold flow disrupted as you get closer in? Is cold streams, is this gas really making it from the kiloparsec into the parsec region, into the black hole eventually, which will take a much longer time to test, but at least in the zoom runs, you can ask yourself, does he actually make it into the parsec region? And this is a zoom of that particular halo, and okay, sorry, the movie is not playing very well anyway, but this is a zoom done with still gadget. So, okay, this is sort of the same images before, low resolution, superimposed by this high resolution zoom that has much better mass resolution and spatial resolution as well. So when you plot your black hole mass as a function of redshift, for example, for this particular halo, which is the only one we've redone in high res for now, there are some differences, but the black hole mass is still growing very high. So there's some delay. This is the black what you get into the zoom, but eventually even gets to be higher. So there are some issues here about exactly what the numerics are doing and so on. And these are really extreme halos of this redshift. They're the most massive things that you can think of. So there's actually even very small variation make a large difference. On top of that, we're actually trying to do these zooms using AMR and therefore go even further in. And we've got one ongoing. This is with Ramses. It's the same halo again. So this is going in further into smaller scales, sort of sub-kiloparsec regions that we are seeing now. This is Gadget, this is Ramses. And of course, the largest differences come into the sort of parsec region scales, where of course with AMR you get a much better idea what the structure of this gas is doing. And here, blob, just a big blob. We don't have particle splitting, so we can't achieve the same resolution. So, but you can start going in, and as of now, and the simulation hasn't ended yet, the Ramses run hasn't ended yet, the growth of this black hole, even down to the small scales, is still dominated by these cold flows, these cold streams that are surviving all the way into the most central region, so that most of the gas that makes it into the, sort of the 100 parsec region is still dominated by gas that is streaming in directly from the cold streams. And this is also because this occurs really fast, and it's not, it gets to the black hole faster than it can be used up to making stars. And just very, very quickly, as I run out of time, we can, of course, with these large runs, in particular in this case, we can look for the population of first quasars and also at properties of their host galaxies. So what are typical star formation rates compared to current constraints or gas mass fractions? This is, the lines are the results from the star formation evolution in the simulations as compared to the constraints on mostly from Carilli et al. From CO of star formation rates in quasar hosts. So these are sort of the Sloan quasars. And there doesn't seem to be a big problem with producing these very large star formation rates as well, just to emphasize that. You grow the mass, but you grow the right stellar masses and with a kind of implied star formation rates. Very last point, when we plot this on an M-black hole sigma relationship that you heard about, these tracks show, again, the quasar population as the matching the Sloan population in terms of luminosity. And you can see that in this plane, they just grow straight up. Okay, so there's, of course, a very, very quick evolution of black hole mass. It grows very, very fast and not matched by a similar evolution in sigma once we compare it to a local relationship. Okay, so black holes grow much faster than their bulges at high redshift, mostly because they can just get onto the salpeter time rather than a standard star formation time scale. So you end up with black holes that are extremely massive compared to the bulge. Okay, and I'll basically pretty much leave it at that. By doing this kind of simulation, you can attempt to learn something about the growth of black holes in these very biased regions, and we can show that it is, I think, possible at the point where we can tell from this set of simulations to achieve critical growth conditions, and that occurs because of this cold stream mode that dominates the growth of these very massive halos at this high redshift. And typically, the black hole will grow first with the bulge lagging behind and growing later, mostly through eventually major mergers and so on, or dry mergers even. And I'll stop at that. Yeah.